Welcome back. Today we cover something called the laws of sines and cosines. Also note that Project 7 is officially assigned at this moment, and it's collected here on class 29, so take a look over there for the date that Project 7 is due. Let's go ahead and start here with the notes. So far, the only triangles we've been able to work with have been right triangles. We want to be able to work with any triangle, not just right triangles. Enter the laws of sines and cosines. First, we need a labeling convention. We use capital letters for the angles, and we use the corresponding lowercase letter for the side opposite a given angle. See the diagram. And so, for example, in this case, we will take capital B and call it this angle, and then lowercase b is the side opposite. Capital C is here, so lowercase c is opposite. And then finally, capital A is here, so lowercase a is opposite. Number 3, here are the two laws. They apply to every triangle. First, the law of sines. Sine of capital A over lowercase a is the same ratio as sine of capital B over lowercase b is the same as sine of capital C over lowercase c. And then the law of cosines. C squared equals a squared plus b squared minus 2 times a times b times cosine of angle C. 4. We'll prove both of these laws later today, but let's first do some examples where we use the laws. 5. A store had a triangular sign made with edges measuring 11 inches, 14 inches, and 18 inches. Find the measure of each angle of the sign. Okay, so let's start by drawing a diagram. So we've got a triangular sign, 11 here, 14 here, 18 here, roughly to scale, but not really worried too much about that. And we want to find the measure of each of the angle of the sign. So let's go ahead and use capital letters for our angles, A, B, and C. Actually, that's not the order that I wrote them in before, so I'll be consistent, although it doesn't matter. And then once we've done that, we want to use the right lowercase letters. So lowercase a goes opposite angle A. So this is lowercase a over here. Lowercase b is opposite angle B. Lowercase c, opposite angle C. Okay, so we're going to dive in using the law of sines. I'll give you, using the law of cosines. And I'll give you hints later on today about how do you know which one to use, but for right now, just trust me, it's the law of cosines. So I'm going to copy this equation down, but I'm going to replace all of the letters that I have with numbers for most of the letters anyway. So c squared, c is 14, so that's 14 squared equals a squared, 18 squared, plus b squared, 11 squared, minus 2 times a, still 18, times b, still 11, times cosine of angle C, which is the only unknown in this equation. So that right there is the law of cosines. And now we'll do a little bit of arithmetic here in order to solve this thing for angle C. Okay, so first 14 squared, I think that's 196. So we're just starting to replace stuff here. So that's 196 equals, I think that's 324, 18 squared. Plus 121 minus 2 times 18 is 36, times 11 is 396. Cosine of C. Before we get too far, let me just double check my arithmetic. 18 squared is there, and then 2 times 18 times 11. The human calculator. Okay, and so now we'll combine here. So we go 196 equals, so we'll add these two things together, 445 minus 396 cosine of C. It is very tempting for some folks and very wrong to subtract 445 minus 396. This guy has a cosine C attached to it. We need to subtract the 445 from both sides. So we do 196, subtract the 445, and we get negative 249. And that's equal to negative 396. There's no room here. Cosine of C. Divide both sides by negative 396. Cancel the two negatives. And we get that. And then finally take the inverse cosine of that number. Okay, again, anytime you hit one of the trig buttons, make sure you know what mode you're in. This problem doesn't specify, I know I said we want to try to be in radian mode as much as possible this semester, but let's just be very gentle on this problem and think about it in degrees, just so we can get numbers that we're a little more comfortable with. So 249 over 396, and it turns out that angle right there is about 51.04 degrees. Okay, so that's angle C. And then so we'll just fill that in now. So we got 51.04. In order to find the other angles, we're going to do the same kind of thing, but then I'm just going to, in my head, start swapping these letters around. The important characteristics of that equation aren't the letters themselves, but the pattern that the letters are supposed to illustrate. So for example, whatever lowercase letter is here has to be the same as the uppercase letter over there. And then once you know those two extreme letters, the first letter you write and the last letter you write, then you know that these letters in here have to be the other two. So that's kind of the pattern. So for example, this equation we could rewrite as a squared equals, and then a bunch of stuff, and eventually cosine of capital A. I know the first letter I write has to be the same as the last letter. And then the other two letters are the ones that go in the blanks here. So this one could be b squared plus c squared minus 2 times b times c times cosine of A. So if we write that equation and then start plugging in, then we go 18 squared equals 11 squared plus 14 squared minus 2 times 11 times 14 times cosine of the unknown angle A. And then you can just follow exactly the same algebraic process that we did down here in order to figure out what angle A is. So I'll just do the highlights on the calculator, but I won't write very much, if anything. So we're doing 18 squared, subtract 11 squared, subtract 14 squared, 7. And then we're dividing by negative 2 times 11 times 14. And then we're taking the inverse cosine of this thing right here. Something seems funny about this. You know, it might be okay. I was a little worried that we had a negative number in there, which means that the angle we get is going to be more than 90 degrees, but it won't be that much more than 90 degrees, and maybe that's okay. So we're going to do inverse cosine of this answer, and we get 91.3 degrees. So we'll say dot, 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 A is about 91.3 degrees. Okay, so we fill that one in. And then you could play the same game, and maybe for practice, you pause the video here and you try to find angle B, writing down some equation that looks like that. Just the letters will change around a little bit. But certainly the easier way to find angle B is to use the fact that the sum of the three angles of any triangle is 180. So 51.04 plus 91.3, and then subtract that from 180. So 3766. Okay, so that's how we use the law of cosines. Notice this is not a right triangle, but that's okay. For right triangles, we have Pythagorean theorem, we have SOHCAHTOA. But up until today, we didn't have anything else really for non-right triangles. And in this case, we can use the law of cosines. And that means that you can take any triangle, and if you know the lengths of the three sides, then you can use the law of cosines a couple of times and find exactly what those angles have to be. Number 6. The Leaning Tower of Pisa was originally 184.5 feet tall, but it now leans at an angle of theta from the perpendicular. All right, let's start drawing a picture here. Okay, so Leaning Tower of Pisa exaggerated looks like this. It says it's, and then we'll put the ground down here at the bottom, and it says it's an angle of theta from the perpendicular. So that tells me that I'm supposed to draw a perpendicular, and then the angle is from there. So theta is here, and Maybe we'll try to give this just a little bit of depth. So that right there is the tower. And then it says, Ian stands 125 feet from the base of the tower on the leaning side of the tower. Also, this was 184.5. So Ian's 125 feet away on the leaning side. So Ian is over here, 125 feet away. And then from Ian's vantage point, the angle of elevation to the top of the tower is 59.7 degrees. So I'm standing on the ground. I look up to the top of the tower, and then the angle between the horizontal, the ground, and the top of the tower is 59.7 degrees. So we're going to try to find the angle theta. So we're going to use the law of sines in this problem. Again, I'll give you hints as to how you know when to use the law of sines versus when to use the law of cosines, but just go with me on this. So here's what it says. It says if you take the sine of some angle, sine of any angle in the diagram, divided by the length of the opposite side, and it's got to be the same ratio throughout. And we can take a look at the law of sines here. It says you take the sine of some angle and divide it by the length of the opposite side. Notice that it's got to be the same letter in both, A and A in this case. Or you could take the sine of angle B, but then divide it by the length of the opposite side, which is little b. And you can do that for any of the three sides and angles of the triangle. Okay, so we know that the sine of the one angle divided by the opposite side is the same as sine of some angle. Now, I don't have any other angles given to me in this diagram. I do have one other side given to me. That's the 125. So I feel like we got to put the 125 down there. And then why don't we go ahead and label the angle opposite the 125. So let's call this guy up here capital A, just so that I can refer to it. So capital A is there. Okay, and that's an equation with just the one unknown in it, so we can solve. Cross multiply is okay, but just multiplying by 125 is better. 125 is it's in the way, it's near the A, and we don't want it there, so it's kind of the greedy thing to do. Instead of cross multiply, just move what needs to move. So multiply both sides by 125, and then we can type that left-hand side into the calculator. And make sure you're in the right mode. Should still be in degrees from the previous problem, so that's okay here. So about 0.585. And then in order to find A, inverse sine of that number. And it turns out the angle is about 35.8 degrees. Okay, so angle A is about 35.8 degrees. So let's move this 185 out of the way a little bit. So up here is a 35.8. And then this side was 184.5. Okay, so does that help me figure out angle theta? Well, it's kind of far from angle theta, but I do know that this is a perpendicular, so that's a 90-degree angle. So if I could just figure out what this angle is in here, then I think we could get theta. But we can find what's in there because we know what's in there must be 180 minus whatever the other angles add up to. Okay, so adding these guys up, what do we get? 95.5. I think that's okay. And so then 180 minus 95.5 is 84.5. So that means that this angle right in here is 84.5 degrees. And we know it's a whole right angle, so that means that theta we can find by just subtracting from 90. So the Leaning Tower of Pisa is leaning about 5.5 degrees from where it was from when it was originally made, which clearly it was originally made to be straight up. Okay, and as far as I know, these numbers are accurate. The measurements, the length or the height of the Leaning Tower of Pisa being 184.5, and then the final answer of 5.5 degrees. I think that that's correct, actually. You can take a look online and look that up. So let's move on to the next page. Number 7, solving a triangle means finding the values of all sides and angles of the triangle. So if you ever see on a quiz or test or homework, solve this triangle, it means find all 3 angles and find all 3 sides. 3 of them will be given to you and you'll need to find the other 3. Solve the triangles below. Part A, little a is 10, little b is 15, and capital C is 75. Okay, so I draw the same generic triangle every time. I don't pay much attention to scale at all. But you got to make sure you put the lowercase letters opposite their capital counterparts. And then we'll start filling in the blanks here. So A is 10, B is 15, angle C is 75 degrees. Okay, so it turns out we want to use the law of cosines here. Again, I'll give you hints soon, but let's try the law of cosines. So C squared equals A squared, 10 squared, plus B squared, 15 squared, minus 2 times A times B times cosine of angle C. So there we go. And with only one unknown in this equation, we can solve it. Really nice thing about this version of the law of cosines, if you're trying to find a side and you have everything else, is that you can just type it in all in one shot. 10 squared plus 15 squared minus 2 times 10 times 15 times cosine of 75. So if I've typed that in correctly, then we've got c squared sitting here. And then take the square root of both sides. And we c is around 15.7. Okay, so that's one answer. So we'll go ahead and fill that in over here, 15.7. And then you're welcome to use the law of cosines again to find angle A and or to find angle B. Personally, I think it's easier to use the law of sines. It's just a simpler equation to plug in stuff and then solve for the unknown. So if I have an opportunity to use the law of sines, then I take it. And now we have this opportunity. Sine of 75 degrees divided by the opposite side is equal to sine of, and then pick your favorite letter, we'll say A, divided by the length of the opposite side. So we can now multiply both sides of this by 10. And then take the inverse sine of whatever we get. So 10 sine 75 divided by, and then instead of typing 15.7, which is a rounded version of the answer, why don't we do second answer? We've got it there, so this will give us the most accurate version of things. And that's what the sine of the angle is, so we'll take the inverse sine of that to find angle A. Okay, and then once we know angle A, then the only thing left to find is angle B. Again, use the fact that it's a total of 180 in any triangle. That's 67.11. Okay, so again, the definition of solving a triangle means find all 3 sides and all 3 angles. In the problems that we're going to see, we're going to be given 3 of those things. So in this case, we were given one side, a second side, and a third was the angle. And then we had to find the other three things, the missing side and the missing two angles. I'm going to put a line here just to indicate as we took some of the space for part B here. Okay, so let's try part B. We don't have a hell of a lot of space for part B, but it's going to turn out that we don't need that much space for B. Okay, I'll draw my same generic triangle. Start filling in the blanks. Still 10 and 15 for A and B. And this time the angle that's given is 75 isn't C like it was above, but rather it's A. Okay, but it seems like a similar enough process. Turns out we can use the law of sines here, so let's go ahead and do that. Sine of A, 75, divided by little a, 10, is equal to sine of, okay, I don't know what angle to pick because I don't have any other angles, but I do have one other side, and that's side B, it's 15. So apparently that means that it's a capital B going upstairs. Remember, it's got to be the same letter upstairs and downstairs when you use the law of sines. Okay, so we'll go ahead and multiply both sides by 15. Trying to find B. So we go 15 sine 75 divided by 10 is the sine of B. And then we need the inverse sine of that, and we'll be done. So let's just do that in one shot. Inverse sine of 15 sine 75 divided by 10. Error domain. Okay, so what's going on here? Well, we know that sine and cosine have some domain issues that we need to, well, sorry, inverse sine and inverse cosine have some domain issues that we need to think about. And apparently we didn't. So let's take a look at that same, let's take a look at that same answer. But I just want to get rid of this inverse sine business. Let's just calculate this fraction. So this fraction is about 1.4. So this means that 1.45 is the sine of B. So what's the problem with trying to take the inverse sine right now? Well, sine only gets up to 1 and down to -1. So looking for an angle whose sine is 1.45 is futile. And that's what the calculator told us when it gave us that domain error. So we can just say no such angles exist. Which means that this triangle that I very cavalierly drew here without paying any attention to scale also doesn't exist. There is not a triangle in the universe that has side of 10, next side of 15, next angle is 75. It is not physically possible to construct such a triangle. And we'll see a little bit more about what's going on there. I'll open up a sketchpad thing in just a few minutes to illustrate why no such triangle exists. But if you try drawing this thing to scale a little bit more accurately than I did, you might start getting some inkling as to why it doesn't exist. Okay, let's try part C. A is 10, B is 15, but now capital A is 25 degrees. So I'll draw my same generic triangle. Fill in the 10 and the 15. 25 degrees up there. Okay, so let's try the law of sines just like we did before. Sine of the angle divided by the opposite side is equal to sine of, I don't know what angle, divided by the opposite side. Well, the only other side that I have is a 15, that's B, so apparently that's also B. Multiply both sides by 15. And then we'll take the inverse sine of this, although I'm feeling a little bit gun shy after we got burned on the last problem, but let's try this. So we go 15 sine of 25 divided by 10. Now, unless this number is between -1 and 1, there's no point in going any further. Okay, so that one, we won't have any domain issues, so we'll do inverse sine of answer. And the angle is about 39 degrees. So B is equal to 39.34 degrees. That's fine. And so I'll fill in red the 39.34 degrees here. That means we could figure out the missing angle, angle C, because we know it's 180 degrees total. Okay, so what do we have here? That looks like 54 and change, so 125 and change, maybe. Let's double check. Not close. What did I do wrong there? 50. So we said, oh, it's 64. It's not 54. You guys can't let me do stuff like that. Okay, 115.66 degrees is angle C, which is fine. So I guess that means that my diagram is wildly not to scale, but that's okay. 115.66. And then in order to find side C, lowercase c that is, we just need to use the law of sines again. So let's go back to the angle that we were given, 25 degrees divided by 10 equals sine. I don't know what to put here. Oh, I do know what to put here. I just learned that angle C is 115.66 degrees. And so that means I can put lowercase c down there, which is great because that's what we want to find. So solving this equation is a little bit more involved. So maybe cross multiplying is an okay strategy on this one. So we go c times sine of 25 is 10 sine of 115.66. And then divide both sides by 25. And then we'll type that in and we'll be done. We'll have C. Okay, 115.66 is second answer, so we'll use that instead of rounding, and then divide it by sine of 25. Okay, so side C is 21.33. All right, so that is that. So we found angle B was up here, and then we found angle C was this guy. So I'm just filling here, this is C. And then side C we just found is down here. Okay, and that's that. So I'll fill in red over here. We just found side C was, what was it, 2133. Okay, and does the triangle make sense just in terms of big sides being opposite big angles? Yeah, 21.33 is the biggest side. It's opposite the 115.66, the biggest angle. The smallest angle, 25, is opposite the smallest side. Okay, so that makes sense. So we're done, except we're actually not done. What we've done here is correct, and this answer is correct. But there's actually more work to be done for this problem. So let's go back up to this. Where are we going to go to? I want to go to this moment right here. And I'm going to put up a line and say, let's just write this guy again. 15 sine of, in fact, I'll do this in a brand new color. So you see it really is independent of the blue stuff that we did to the right. 15 sine of 25 divided by 10 was the sine of B. Okay, so I'm just going to type this again. We'll get the same 39 degrees that we got before, but let's just pull it up. So we go 10 sine 25 divided by, see, that's supposed to be 10, but the first one was a 15. Okay, and then we wanted the inverse sine of that answer. And that's our 39 and change. Okay, so what else is there to say? Well, really we were solving a trig equation here. And the equation we were solving was sine of B is roughly supposed to equal, what, 0.634? And we found that one answer is 39 degrees, but we spent a lot of time talking about solving trig equations. And we saw that generally we actually expected not just one answer, but two answers between 0 and 360. Sure, infinitely many answers if you allow the angles to go on forever, but we often got, almost all the time, we got two fundamental answers. And this is just one of them, the 39 degrees. Calculator will never give you the second one. We had to think about symmetry of the unit circle, or we had to draw a graph of the sine function. So let's draw the unit circle here. And here we want the sine to be about 0.6. The sine is the x or the y. We know the sine is the y. So if I want the y coordinate to be 0.6, then, so there's halfway, so maybe 0.63 is up here somewhere. So we come over to this guy, so that's a 0.63. And we connect in here, and we found that this was about 39 degrees and change. But there's another angle on this unit circle that has exactly the same sine value, has the same y value. And we want the same y, so we'll keep going here to the left, and we'll find this point over here, which means there's another angle that we can think of. I'll draw it here in red. It's this angle. So by symmetry, we know that this little guy in here, the reference angle, is the same 39 degrees and change that we got before, which means that the red angle is 180 degrees subtract, because we got that straight line, subtract the 39 point, what was it? 34. So that means that the red angle is 140.66 degrees. 140.66 degrees. So if I come over here and I typed in sine of 140.66, then we get 0.63392, which is what we got up here. It's not perfect out here because I rounded the 0.66 because it came from a rounded 0.34. But gosh, 140.66 is another perfectly good solution to this equation. 39 degrees is not the only answer. 140 degrees also works in here. So what do we do with that other angle? Well, I'm going to draw another triangle. So I'm going to copy my not to scale blue triangle up here. So same A, B, and C. And we still have that A is 10, B is 15. And then little a, or capital A, is 25 degrees, just like we had before. But now, instead of filling in 39 degrees for angle capital B, that's what we found for this equation. Instead of 39 degrees, 140 degrees works just as well. So for B, I'm going to put 140 degrees. So this is another potential angle B. So we're going to put 140.66 degrees. And then we got to do the work we did before, but with this new 140.66. It's a perfectly good angle. And in fact, this is a completely separate triangle that also satisfies the given conditions, the 10, the 15, and the 25 degrees. So let's go through the process again now. Let's go ahead and write down sine of, what do we do here? Actually, yeah, so let's actually find angle C at the moment. So we know angle C is 180 minus the 25 minus the 140.66. Okay, so about 14.34 degrees. So let's fill that in the triangle. 14.34. And then we're going to use the law of sines to find lowercase c. So you have a choice here. You can either use the 25-degree angle. We definitely have to use the 14 because that's the one that's opposite the unknown. But then we have a choice to either use the 25 or the 140. Always use the not rounded ones if possible. So let's use the 25. And in fact, we're going to do the algebra here a little bit more efficiently. Since we're trying to find little c, I actually want little c to be on top. So that's what I'm going to write in terms of my equation. C over sine of the angle is equal to 10 over sine of the angle. So the law of sines is written, up above or on the previous page, I should say. But all those ratios can be flipped over, and then it'll still have true equations. So here, we don't need to cross multiply. We could just multiply both sides by sine of 14. Okay, so this is going to be side C, and we'll type it, and that will be the end of this problem. 14.34. And we get about 5.86. So that's the last piece of information here, 5.86. So I'll color in a different color now that we have angle, where are we now? We have angle B is equal to 140.66. And then we found out that angle C was 14.34, and then side little c was 5.86. Maybe I'll try to make this guy a little bit bigger. Okay, so in this case, two perfectly good triangles. We've got them both drawn not at all to scale, but they both satisfy the givens. They both have a side of 10, side of 15, and then the next angle is 25. So here's a 10, 15, and 25 with these other three numbers in red. But here's a perfectly good other triangle with a 10, a 15, and a 25, and then three different numbers in red. And it's our responsibility to make sure that we find all the legitimate triangles. There'll never be more than two. But if there are two triangles out there that satisfy the givens, it's our job to find both of them. Okay, number 8. A couple of observations about our two new laws. Part A, write down the other two versions of the law of cosines. Okay, so the law of cosines that was typed on a couple of pages ago started c squared. So there's another one that starts a squared equals, and yet a third one that starts b squared equals. So we wrote one of them already, but maybe pause the video, see if you can fill in the two equations using the pattern of the law of cosines. Okay, part B, we use the law of sines if we know all three sides. We'll call that SSS for side, side, side. Or two sides and the angle between them. We'll call that SAS for side, then angle, then side. So let's see if that's when we used the law of cosines, when we had side, 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 or side, angle, side. So taking a look at this picture here in number 5, the givens were just the three sides. We didn't have any of these red angles. We had to do work to get those. So when you have side, 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 you must use the law of cosines. That's exactly what we did. Let's take a look down here at this picture. The givens in this picture were this side right here, this angle right here, and this side over here. That's not a side angle side. So we didn't need to use the law of cosines there. Taking a look at this picture, what did we have? We had a side and another side and the angle in between. Side, angle, side. And when we have that, we have to use the law of cosines, which is exactly what we did. So then I guess what I'll say, it's written here. Yeah, here in part D, we use the law of sines. If we know two sides and the angle opposite one of them, you need to know two sides and the angle opposite one, side, side, angle, or two angles and the side opposite one of them, angle, angle, side. I guess I'll write down, well, I don't have that memorized. Here's what I have memorized. If you have a side angle pair, then you can use the law of sines. And that's the only thing that I know that guides me as to which law to use. So if you happen to have a side and the angle opposite, you get to use the law of sines, and that's great because that's the easier equation to use. But if you don't happen to have a side angle pair, then you must use the law of cosines. So taking a look in this picture here in part A, did we know a side and an angle opposite? All we had was the green information here. We had a side, but we didn't know the angle opposite. We had an angle, but we didn't know the side opposite. We had a side, but we didn't know the angle opposite. So we didn't have a side angle pair. So we couldn't use the easier law of sines. Therefore, the default is law of cosines. Coming down here, we have a pair. You have the angle and the side opposite. As soon as I see that, I say, all right, I get to use the law of sines. And that's what we did. And the same thing in this problem, the green information was given, and we had, again, a pair, an angle and the side opposite. Part C, what happens in the law of cosines if C is a right angle? Okay, so I'll write the original version, not the one that's up there already, but the C squared version. So if angle C is a right angle, then we get to put 90 degrees right here. But we know that cosine of 90 degrees, how much is that? C squared equals A squared plus B squared minus 2 times A times B times, our cosine of 90 is 0. So actually the whole last term drops out. It all goes to 0. And we just get C squared equals A squared plus B squared, which is better known as the Pythagorean theorem. So what that means is that the law of cosines generalizes the Pythagorean theorem. And in fact, you can scratch the Pythagorean theorem from your brain right now if you just add to your brain the law of cosines, because the law of cosines works all the time, including when you have a right triangle. And if you have a right triangle, it reduces to the more widely known Pythagorean theorem. E, warning, there may be ambiguity if you are in the SSA case. Let's have a look at the GSP file, and you will find this file in Moodle, but let's have a quick look at it here. Okay, so here's the file. What's given in this problem is S, S, and A. So a side, and then the next side, and then the next angle. So this side right here is fixed. I will never make that thing longer or shorter. This side right here is also fixed. I won't change the length of that. And then finally, this angle right here is fixed. I won't change that angle. But what I could change is this angle. That's free. I could change how long this bottom side needs to be. And I could also change this angle over here, which really isn't defined at the moment. So what I'm going to do is take this guy and rotate it, because it's not a triangle yet. But I'll put it over there, and I will just point out that this length has not changed, nor has this one, nor has this angle. So there's the S and the S and the A. And here is one perfectly good triangle with some excess stuff over here you can ignore. But there's one perfectly good triangle with that side length, and this angle measure. But if we take this guy and rotate it around this way, then we see there's actually another point right in there where that's still the same side length that we had before. That's still the same side length, and this angle is the same. And there's a perfectly good different triangle that has the right side, and angle. So we had one over here, and then a completely separate valid one over here. And that's exactly what we had in this case right down here. We had this one triangle with a side, and an angle. And then we had this other triangle with the same side, and angle, but other stuff had changed around. This is what the two triangles look like. One of those guys and one of those guys. Okay, so what if we take this guy right here and we make it shorter? So I know I'm cheating because I said I would never make this side length any shorter. Well, okay, it's shorter now, but now we're going to fix it at this new short length. So if we make it just the right length so that this guy barely touches down there, then actually there's only going to be one triangle. It's going to be a right triangle. And it's not going to touch over here, and it's just going to touch once barely there, and then it won't touch again. So it is possible, depending on the relationship between the two side lengths and the angle, for there to be just exactly one triangle there. What happens if I make this side shorter still? But now I won't change it again for a little bit. If I rotate, no matter what happens, I cannot reach that bottom side. And so this is a case where there's exactly 0 triangles that exist with this side length, and this angle measure. And that's what we saw here in part B. But these two sides and that angle, imagine swiveling this thing. I think we'd have to rotate that in our mind. So you might want to redraw that if you really want it to look like this guy. But that's what's going on here, is that the one side was too short. That 10 was too short to actually have any chance of reaching this side over here. Okay, so sometimes you have 0 triangles. Sometimes you have exactly the one triangle, like over here. Sometimes you have 2 triangles, like one there and a second one there. All right, what happens if we just keep going forever? Let's make this guy really long. Okay, so we've got a triangle out here. That's one. That's fine. But then what happens? Well, there is no second triangle. This side is too long. It's longer than side AC. And that means there's actually not a second triangle. So in this case, we're back to another unique triangle case. So we could have 0 triangles, or exactly 1, or exactly 2, or exactly 1 again. You don't need to memorize it, but I just want you to understand there's a visual happening behind the scenes. It's not just playing with numbers here, but there's actually physical constraints that tell you how many triangles you might have. Okay, number 9 is a proof. And so before I do the proof, I'm just going to say the activity is in your book. And again, you're going to give it a good shot before you look for me doing the video for it. So if you want to see the proof, then hang out and I will prove these 2 laws for you right now. But if you don't really care about the proof, you can stop watching this video. Nothing that I do here from here on out is fair game in terms of the upcoming test or final exam. Okay, so let's prove these 2 things for you looking at this one diagram. So we've got our generic right triangle. Notice that lowercase b is opposite side b, lowercase c is opposite side c. Okay, what side should be down here? Well, that whole thing is lowercase a. I didn't write lowercase a, but I did call this little piece here x, which means that whatever is left over must be a minus x, because the whole thing is a. And this little piece here is x. So a minus x is there. Turns out I need to draw a height or an altitude in my triangle. So I drew that thing in there with right angles on either side and call the length of that one h. Okay, so let's give this a shot. Ultimate goal is to prove each of these 2 equations. We'll do them one at a time. Okay, first one I want to do is the law of sines. So I'm going to write down sine of c, and I want you to focus on just this one triangle right here, which is a right triangle, which means we can use SOHCAHTOA. And so if we want to find the sine of c, we'll use SOHCAHTOA, opposite over hypotenuse. Opposite is h. Hypotenuse of that triangle is b, and we're done there. And now I want to find the sine of capital B. And for this one, I want you to focus on this triangle here, which again is a right triangle. So we can use SOHCAHTOA to find the sine of B. Opposite over hypotenuse. Opposite in the green triangle is h, divided by hypotenuse is c. Now both of these equations that we just wrote down have h in them, so for kicks, why don't we just solve for h in both cases? So multiply by b over here, and then multiply by c over here. But it's the same h in the picture, and so it's the same h in both of these equations, which means we can merge these 2 guys together and come up with one brand new wonderful equation. B sine of c is c sine of b. It's a little bit of a tongue twister, but the important thing is actually it's really close to the law of sines. So how about we divide both sides by, I don't know what, BC. BC. So what does that mean? Okay, so on the left-hand side, the b's cancel, and on the right-hand side, the c's cancel. That's nice. And then we'll write down what we have left. It's the sine of c divided by little c is equal to the sine of b divided by little b. Hooray. That is one of the parts of the law of sines. It's right there. Okay, so how do you get the a in there? Well, you can, if you want to be kind of efficient and mathy, then you just change the letters and you say, okay, well, it didn't have to be a. That one could have been b, and this one could have been a. And there, all of a sudden, you're going to get the a in there. But if that doesn't feel good to you, then what you need to do would be to draw a different altitude. We drew the altitude from a over to here. We would have to draw a different altitude. For example, let's see, so the other altitudes are actually outside of the diagram, so it's going to look a little bit funny, but if I were to say extend, can I extend this side right up here and then draw from point B going perpendicular to that side over there, then you can play the same game that we just played with two different right triangles giving you two sine equations, and one of them will have capital A in it. So that's how you can bring A into the party. Okay, we'll move on to prove the law of cosines. So in order to prove the law of cosines, what I want to do is, again, focus on those two triangles that I've highlighted in red and green. And we're going to use the Pythagorean theorem on these two triangles. They're both right triangles. So in this triangle right here, x squared plus h squared equals b squared. And then in the other triangle over here, h squared plus a minus x squared equals c squared. So let's write those two equations down below. Okay, so we'll write them down here. Okay, so the first one we said was x squared plus h squared equals b squared. And then the other equation is a minus x squared plus h squared equals c squared. So that's just two applications of the Pythagorean theorem. Okay, let's go ahead and expand this bottom equation here. This a minus x squared, write it twice and then FOIL. We get this. And then what I want to do is take these two equations and subtract. Let's go ahead and do the bottom equation minus the top equation. So if we do that, then the first thing I see is a squared minus 2ax. When I subtract this guy minus this guy, the x squareds cancel and the h squareds cancel. That's great. And then we'll subtract on this side and we'll just write c squared minus b squared. Okay, so that's subtracting the bottom equation minus the top equation and canceling. Okay, let's go ahead and move the b squared over to the other side by adding. So add b squared, I'll go ahead and put it in here because I know where we're going, 2ax equals c squared. So that's actually getting pretty close to the law of cosines. But the thing that I don't want in the law of cosines is this x business. So let's come up to the triangle and see if we can finagle a way to get that x out of the equation. Take a look at the red triangle and figure out the cosine of angle C. Again, it's a right triangle, so we can use the law of cosines. So adjacent over hypotenuse, x over b. So there's an equation with x in it. And why don't we go ahead and solve this equation for x. So x is equal to b cosine of c. Okay, so let's take that and replace the x that we have down here. This x right here is the same as b cosine of c. I'll write everything else. Just copy everybody else straight down. And just like that, the law of cosines. So there's a proof for that version of the law of cosines. Again, you can get the other versions by just changing the letters or drawing different altitudes. I really like the proofs. I think they're very clean and very nice, and they justify using these two quite strange looking laws. But what I quite like about these two proofs is that they both use exactly the same diagram. So from one diagram, you get two very powerful theorems in math.